All right, so we're looking at the squeeze theorem. The squeeze theorem is used in problems where we can't find the limit just looking at it. So, and you can't use your like algebraic, properties that we've done before. So if you look at this one, if I try to do direct substitution to find the limit of x squared times cos of 1 over x to the third, I'm going to have a 1 over 0. And I can't do that. So, and then there's not like, I can't factor it. I can't use a conjugate. It's not a complex fraction, all that stuff. So the normal things that I want to do aren't going to work. You typically will see squeeze theorem with sine or cosine, sometimes tangent, but you're going to see these with trig functions a lot. I'd say that's pretty common. So what we're going to go ahead and do is we're going to learn how to squeeze a function like this. So on here it asks you to graph f of x, which is x squared, and h of x, which is negative x squared. We're going to graph those first because those are the easier ones. So I've got 1, 1, and negative 1, 1. So this is me graphing x squared. 1/2 times 1/2 is, if I plug in 1/2, I'd get 0.25. So we'll go ahead and just draw like a sketch of that. And so this right here is f of x. And then we're also going to draw h of x. So just the flipped version of the same thing. And then last, we're going to go ahead and graph g of x, and this one I'm going to use my calculator for. So I've got x squared and then cos of 1 divided by x to the third. And to graph this, I'm going to make sure that my calculator is in radian mode. If you were in degree mode, then you'd have to be ready to have outputs in the hundreds. And in calculus, actually, for future reference, we will always be in radians, always. I'm going to change my window to match the window of this. I'm going to say -2 to 2, -2 to 2. I could even change it and make the step go by 0.5s maybe. Make this scale go by 0.5s. And so what's happening here is this is what we talked about for one of our situations where the limit doesn't exist. We talked about what happens if you have an oscillating function. And so those are, and we know that cos functions and sine functions oscillate. They bounce back and forth between 1 and -1. Now this oscillating function looks like as it oscillates, it's going to get closer and closer to the x-axis. And actually what we can do is change the window from like -0.5 to +0.5. Oh, that was dumb. Looks like I missed it one of the ways. There we go. So you can see that when you zoom in, you like really see that oscillation. Our calculator's having a hard time with those decimals and getting all that accuracy in there, but you can basically see what's going on. So I'm gonna go ahead and zoom back out. So we're gonna draw a sketch of this. I can see that it's coming from above and then it's doing that oscillation, then going back up. And if you want, we can actually go ahead and graph x squared and -x squared just so we can see those parabolas in there. So you might be guessing where the squeeze theorem comes from. If you look at this, that oscillation is actually squeezing right in between those two quadratic equations that we have. So I'm going to draw a sketch of this. It's not going to be perfect. So it looks like it starts from above, and it comes right by 1, it looks like, or -1, I guess. And then it comes down, and it bounces, and it goes, something like that. And then so my other side's not going to be as good, I don't think. Something like that. Okay, We can call that good. So there's our, oh goodness. And this function is our g of x. So that's our function that was squeezed. All right, so here is how we do a problem where we're trying to find the limit of something we can't plug 0 into, but we can squeeze it or sandwich it. We're going to go ahead and say that our function x squared times cos of 1 over x to the third was squeezed in between negative x squared and positive x squared. So if I can come to a conclusion about the limits of these two, if I can say the limit as x goes to 0 of negative x squared, and I can solve for that limit, and then I can do the limit as x goes to 0 of positive x squared. If I can evaluate those limits and I get the same number, then I can say, well, this is between them, so it must be that same number as well. So I have no problem plugging 0 into negative x squared. That's just going to be negative 0 squared, which is 0. I can do direct substitution in this one as well. So since they're both approaching 0 at 0, and we squeezed this oscillating curve in between them, then we can make a reasonable conclusion that the limit as x goes to 0 of x squared times cos of 1 over x to the third is also 0. Right? So the squeeze theorem is if function f of x is less than or equal to the function g of x is less than or equal to the function h of x, if you can make this sandwich or if you can squeeze it, when x is near c, and when they say that phrase, you'll see that multiple times in calculus. When they say x is near c, they're talking about that value right there. So in this case, our c value was 0. So near c, except maybe at c, and the limit as x approaches c of f of x is the same as the limit as x approaches c of h of x, which equals L, right? So in this case, we'll say the limit as x approaches 0, and the limit as x approaches 0 was equal to 0. Then the limit of the function that was in between them is also going to equal that same L value. All right, so here's a picture of the squeeze theorem, a different idea, or a different picture, but you kind of get the idea. You can see it's the same. So if we are unable to evaluate g of x, but we can look at f of x and h of x at that specific x value, and we're going to call that x value c, and we have a y coordinate of L at both of those places, or we have a limit of L at both of those places, then we can assume that since g is in the middle, it's going to have that same limit. Right? This theorem is sometimes called the sandwich theorem because you're literally making a sandwich between those two. Or the pinching theorem. And I will say pinching is not very common. Sandwich theorem, yeah, you'll hear that. Pinching theorem, not so much. But it's good to know at least. Okay, so next page, or the back side, has some examples. So suppose that we can say that some function f of x is in between these two other functions, and we want to know the limit, then we just need to check the limit of each of these functions. So the limit as x approaches that same c value, which in this case is -1, the limit as x approaches -1 of x minus 3 is going to be, I can do direct substitution to get -4. And then over here, I'm going to do the same thing. The limit as x approaches -1 of x squared plus 3x minus 2. So I've got -1 squared, which is 1. 1 minus 3 minus 2 is -4. So since both of those have a limit of -4 and f of x is some function that's between them, then that means that f of x also has a limit of -4. So then I could make the conclusion that the limit as x approaches -1 of f of x also equals -4. All right, use the squeeze theorem to evaluate this one. Now, this problem is going to feel a little bit more tricky because they didn't give us the functions to squeeze it with. They didn't say this is what you're going to use on the bottom, this is what you're going to use on the top. So what we have to do is we have to figure out a way to write an inequality. And I'm going to go ahead and start with just having sign. I'm going to say just sine x. Okay. Now, one thing I know about sine x is that the outputs bounce between -1 and +1. So I can start there. And this is an example I'd say you're going to do a lot of problems you're going to do just like this, okay, if you're coming up with the function on your own. So sine of x jumps between -1 and +1. Now, it doesn't matter what I plug in for x. I can like plug in anything. So I'm going to say sine of 1 over x squared plus 1. No matter what the graph is, unless it has a coefficient. If it has a coefficient, it could bounce between something else. But no matter what I plug inside, it's always going to bounce between -1 and +1. So at this point, I'm a lot closer to having this in the middle. Now I can go ahead and I can figure out how to get that x to the 4th in the front. And so I'm going to multiply by x to the 4th and multiply by x to the 4th and multiply by x to the 4th. And you have to be careful here because you have to think about whatever I do to this inequality. I have to think, could I be multiplying or dividing by a negative? Because if I could, I need to change my symbols. Now, if I multiply by x to the 4th, it doesn't matter what I plug in for that. That is definitely going to be a positive number. So I've multiplied by a positive. That means I can keep the inequality symbols the direction that they were. All right, so now I can go ahead and use the squeeze theorem to finish this problem. So now I can take this piece and I can say the limit as x approaches 0 of -x to the 4th is 0. The limit as x approaches 0 of x to the 4th is also 0. And so I can make my conclusion that the limit as x goes to 0 of x to the 4th times sine of 1 over x squared plus 1 is also 0. Yes, this problem could have been direct substitution if you're looking at it. This is not like undefined. You can really plug 0 in there and do sine of 1 and that's okay. However, we had to do it because they said use the squeeze theorem. So. All right, so we're going to do another squeeze theorem problem. So this one says the limit as x goes to infinity. This one, we already kind of know the answer because we have learned n to the n FEPL. So if you think about the way n to the n FEPL works, it would tell you that the top is going to bounce back and forth between that 1 and -1 for this, so that's like not growing very fast, and that the bottom is linear, so the bottom definitely wins. And that means we know that the limit is 0, but it doesn't say use n to the n FEPL to evaluate this limit at infinity. It says to use the squeeze theorem, okay? So we have to use the squeeze theorem, and so I'm going to start with saying that cos x is between -1 and +1. And now I need to put things on all three sides, if you will. I have to put things in all three pieces to get it so that the inside looks like this. So the next thing I want to do is I'm going to multiply by a -1. I wasn't moving until my light turned off in my classroom. That's depressing. I had to get the light back on. Okay, so I multiply by that -1, and that makes this a +1. It changes my inequality symbol, and it makes this a negative cos. All right, so now what I'm going to, oh, I was multiplying, not adding. -1. Okay, so now I need to get the 3 in the front, so I'm going to go ahead and add 3. So 3 plus 1 is 4. And now I want to get that over x plus 2 for all of these. So I'm going to say divided by x plus 2, divided by x plus 2, divided by x plus 2. Now, I don't know, like depending on what I plug in for x, you'd say, well, that could be a negative number, it could be a positive number. Well, think about the limit you're evaluating. You're going to be plugging in positive infinity. So if I plug in a positive infinity, then I'm definitely not going to be dividing by a negative number. Positive infinity plus 2 is definitely positive. So that means that my inequality symbols can stay exactly the way that they were. Okay, so now I can go ahead and evaluate these two limits on the end. So the limit as x goes to infinity of 4 over x plus 2, well, I know that's 0 because that's 4 over infinity. And for this one, the limit as x approaches infinity of 2 over x plus 2, I know is also 0 because I have 2 over infinity. And so just like we kind of predicted using n to the n fepal, we can say that the limit as x approaches infinity of 3 minus cos x over x plus 2 equals 0 as well.